Hi, my name is Patrick Kutch. I'm the I/O virtualization TME for the LAN Access Division at Intel Corporation. In this presentation, I'm going to give an overview of Intel VMDq technologies and give you a quick demonstration of it in action. So first of all, let's talk about how Ethernet is is used in a virtualized environment today. In most cases, what happens is that when a packet comes in from the Ethernet and it hits the physical Ethernet controller, the NIC, the data is transmitted up to the VMM, up to the virtual machine monitor, and then the data is examined by a software switch within the virtual machine monitor. And this virtualized switch, the software-based switch, examines the destination MAC address for each one of those incoming packets to determine which virtual machine that packet is supposed to go to, because each one of the virtual machines has its own unique MAC address. So a packet comes in and it's examined within the software, and then it's sorted and then copied to the appropriate virtual machine. This works very well, and it scales to hundreds of virtual machines pretty easily. You can have hundreds of virtual machines all sharing the same virtual NIC. In the demonstration we're going to do today, we're going to show 8 virtual machines all using the same Intel 10 gigabit Ethernet controller. The problem is that this software sorting comes with quite a bit of overhead, because the packet's coming in, especially 10 gigabit, is coming in as fast as it can, and then it hits this software-based thing, and it has to look at everything, so that slows it down. It's quite the bottleneck, as you're going to see in the demonstration in a few minutes. Intel developed a technology called Intel VMDq, which is virtual machine device queues. And what this does from a high-level view is it moves the sorting from software down into hardware within our Intel VMDq NICs. And from a high-level view, what we have is a set of queue resources within our NICs and a little sorter, a layer 2 classifier sorter, a little switch within there, if you will. And this switch is configured by the hypervisor, and it says, the VMM says, okay, I want all packets with this destination MAC address to go into queue number 1, this destination MAC address to go into queue number 2, and so on. So now a packet comes in, it reaches the sorter, the packets are sorted and put into the appropriate queue, and then the packets are sent to the VMM, and an interrupt is fired. Each queue has its own unique interrupt. So when a packet from queue number 1 is sent up to the VMM, an interrupt associated with queue number 1 is fired. The hypervisor then, the VMM, gets this interrupt, and it says, oh, I know that this interrupt is for queue number 1, and I also know that I've configured it so that all the traffic for queue number 1 is supposed to go to virtual machine number 2 or virtual machine number 1, however it's configured it. So now the hypervisor, the VMM, no longer has to sort this incoming packets. All it has to do is copy it up to the virtual machine. So the sorting is all done in hardware now. So this accelerates the traffic dramatically. There's no longer this so much of a bottleneck there in software when the packets are being received. So that's a high-level view of Intel VMDq, very high level. So now let's do a quick demonstration of it in action. So what we have is we're going to have 3 systems involved in this quick test. We have an Intel Foxcove server here running 16 cores and 16 gigabits of RAM, and it's got an Intel 82598 10 gigabit Ethernet controller that is going to be transmitting and receiving the traffic from a transmit system. This transmit system is going to be sending NTTCP traffic to each one of the virtual machines. Each one of the 8 virtual machines has an NTTCP receiver in it that's going to be receiving these packets as fast as it can. And then as soon as an entire packet comes in, it sends back a response saying, send me another packet. So that's all this application does, is it receives big chunks of data, processes it, sends back a response saying, send me more data. That's all it does. And the last system is a console system that shows that allows me to remotely access each one of the virtual machines. And we're running ESX Server 3.5 Update 4 on this. So let's go take a look at the actual server for a second. So this is the screen for the Intel Foxcove running ESX. This is the ESX top is running, showing the throughput of the data being received. So down here you can see that each one of the virtual machines is receiving around 360 megabits per second. This here is the total throughput for all the traffic being received on that 10 gigabit controller. So you can see, even though data is being transmitted on a 10 gigabit link, we're only getting around 2.6, 2.7 gigabits per second on this link. And that's because everything's being sorted in software right now. Now let's take a look at the CPU utilization on this system. Up here along the top is the CPU utilization for each one of the individual 16 cores. And here is the important number. This is the average CPU utilization for the entire server. So right now we have these 8 virtual machines getting this data and processing as fast as it comes in. And we're using around 20% of the CPU, all the total CPU for the system. Let's go over and take a look at an actual virtualized system. This is a virtualized Windows Server 2003 running this application that's receiving the data. Here is a view of the task manager showing the network throughput. So as you can see, it's a virtualized 1 gigabit controller. It's running at around 360 megabits per second, just like what we saw in the ESX top view. And it's using around 20% of the CPU, just like we saw. So what we see here in the virtualized Windows OS is exactly what we see over in the ESX window over here. So now let's enable VMDq really quickly, and all this does is this is a script that unloads the driver and reloads it with the parameters to enable VMDq. When that happens, then VMware ESX goes off and it configures that sorter and configures all the interrupts and configures the queues. So now let's take a look at the total throughput here. Recall that this is the area that shows the throughput for each one of the individual virtual machines. It was at 360 megabits before. Now we're averaging over 1 gigabit per second per virtual machine. This here is the aggregate, the throughput for all of those virtual machines on that NIC, and it's running at over 9.2 gigabits per second. And all we did was enable VMDq to make this jump happen. So we went from 2.7 gigabits per second to 9.2 gigabits per second just by enabling VMDq. Now let's show the CPU utilization, which is again just using ESX top. And again over here on the right is the important one. We went from 20% utilization up to over 60% utilization just by enabling this technology. And for a more graphical representation, we'll go back to our virtualized server. This is before VMDq is enabled. We enabled VMDq, and the utilization, the network utilization, went up to over 100%. It only shows 99 because it only thinks it's a 1 gigabit controller. And the utilization now is at 40, 50, 60% utilization for that virtualized CPU. Quite a dramatic jump just by enabling the technology. So in summary, Intel VMDq technology offloads the sorting of those incoming packets from the software layer, from the software switch within the VMM to hardware within the Intel VMDq NIC. By doing that, you increase the throughput of the data dramatically, allowing I/O-intensive applications to run much more quickly and have much better utilization of the CPU resources on the server itself. So we jumped from 2.7 gigabits to 9.2 of throughput and 20% CPU utilization up to over 50% CPU utilization simply by enabling this technology. Thank you for your time. I hope you found this useful.